cooling system. Yeah, cool. I like that. And what about when you get cold? Is it part of the thing that keeps you warm?
Yes, it will warm you up.
So heat control. Cool. So protection, defense mechanism, heat control. I love that. I love that. Miss Hunter, what is the integumentary system?
Hair, skin, and nails.
Awesome. Can you tell me why, something good about it besides, I don't know, besides stuff we've already talked about, temperature control and protection and kind of defense from outside foreign invaders?
Well, I was gonna say the nails, I don't know, they used to be long. They used to protect you too. Or I also was gonna say hair, but for like temperature control, but I guess they already said that.
Well,
but the hair
but,
on your head.
But by the way, you actually do make an interesting point. It's not what I was looking for, but you're dead on right. The hair on your head, they're pretty sure is there. Your largest loss of heat on your body is through your head. The if you are worried about being cold, the number one thing you want to do is put on a hat. And so the hair on your head is actually very important. And that was not the type of temperature control we were talking about. We were talking about sweating and things like that. So you're right. That's excellent. And I love the way you're thinking. How do you get vitamin D in your body, by the way?
You absorb it from the sun.
Oh, the sun. Yes. So your skin actually helps you create vitamin D. Cool. I love that answer. Yeah. Thank you. Awesome, awesome, awesome. Okay. Miss Bilotic, what is the integumentary system?
Hair, skin, and nails.
Cool. Can you tell me even something that's already been said that it does for us?
Well, with the absorbing, I was gonna say, like when you put on lotions, that might help because that has vitamins in it sometimes.
That's true too. That is true. And by the way, stuff you put on your skin can get in your body. It's meant to be waterproof, but there is some stuff that can go through your skin. That's actually very true. And we also know that our skin helps us expel things too. Believe it or not, about 2% of the toxins in your body come out through your sweat, which is why you can smell things on your sweat like garlic, alcohol, things like this kind of come out through your sweat too. Thank you. All right, we'll take that. I'll take it. I feel like I'm forgetting. Oh, yes. Mr. Kandars, what is the integumentary system?
Skin, hair, and nails.
And why is it very important to a massage therapist? And I don't mean to the client. I meant what's in the skin that's very important to a massage therapist?
Deeper tissues.
Deeper tissues, that's true. How do you feel your client?
Through their skin.
Yes, and through your skin. Your skin is where your sensory organs are.
Yeah.
So they have to hook into your nervous system, don't get me wrong, but that's where all your sensory organs are. So skin gives you a sense of touch. Cool. So that's the integumentary system. That's awesome, everybody. The other system we studied was the skeletal system. Yeah? Who wants to tell me what makes up the skeletal system? I mean, there's one obvious thing, I hope. Bones, thank you. That is, by the way, if you had to just give a one-word answer.
My mic is on?
Your mic is on. That is a good one-word answer, though. Yeah, bones. Anything else? What attaches bone to bone?
Ligaments.
Ligaments, thank you both. Ligaments. So, bones, ligaments, and the associated joints. Bones, ligaments, and the associated joints. Where the bones articulate the joints and the ligaments that tie bone to bone. That's your skeletal system. Bones, ligaments, and the associated joints. Miss Monreal? What is your skeletal system?
Bones, ligaments, and joints.
Yeah, cool. Bones, ligaments, and joints. Give me one reason to have a skeletal system.
Because we would be a pile of goo without it.
Good. Okay, so structural support. Just structural support. Just the fact that it's the structural support for our body. I like that. Miss Cooper, what makes up the skeletal system?
Well, bones. Would it also
Would it also be muscle?
Hold on, Miss Cooper. Let's go back. Miss Monreal, what makes up the skeletal system?
Bones, ligaments, and joints.
Bones, ligaments, and joints. Miss Cooper, what makes up the skeletal system?
Tendons?
Tendons attach muscle to bone. They're part of the muscular system that we're going to study today. So what makes up the skeletal system, Miss Cooper?
Bones, ligaments, and joints.
Cool. All right. Can you tell me anything the skeletal system might do for you?
What it can do?
Yeah.
I mean, it gives shape and support to everything inside of it.
Okay, we'll take that. So again, structure. Miss Yanez, what is the skeletal system, and tell me something it does.
It's bones, ligaments, and joints, and it helps with movement.
It does help with movement. It helps with movement because it is the levers of your body, right? My arm moves like this because a muscle hooks to it, but there's muscles hook into a bone. It's the steel girders, the 2x4s, the whatever of your body. Absolutely. So now we've got structure and movement. It's the levers of your body. It doesn't move the levers, but it's the levers of your body, right? Very good. Miss Torres, can you tell me what the skeletal system is and something else it does?
Bone, ligaments, and joints, and I think it protects our organs.
It does. Okay, so now we've got structure, protection, and levers. That's good. She's right. Like the rib cage and stuff like that protects our organs. Cool. Miss Hunter. Cool. By the way, thank you for the nod, because then I know you heard me. What's the skeletal system and something it does?
It's I was about to say hair, skin, and nails. It's bones, ligaments, and joints. And something it does. Well, I feel like I don't know, but I think that muscles attach to the bone, and it's like a site for it. So if it was, I don't know, possibly there wouldn't be no muscles without them. I don't know. I made it too difficult.
You made it too difficult, but you're right. Actually, by the way, no one system would exist without another system, right? They all interrelate. So along those lines, is there any way that the skeletal system helps out the circulatory system? That's the system with your blood and stuff in it. Is there any?
Yeah, I think it's part of it, right?
Well,
Because the blood is created in the bones, right?
Oh my God! I forgot all about that. That's right. Your skeletal system makes the blood in your body. Thank you. Thank you for getting us back on track. I appreciate it. Okay, so it protects me. It gives me stability. It's the levers of my body. It protects my organs, and it makes my red and white blood cells. The stuff that fights off bad guys is the white blood cells. The stuff that lets me breathe right now is my red blood cells. Yes. Very cool. And those are made inside the long bones of your body. That's fantastic. All right, so we've covered two systems so far, right? Yes? Yeah? Oh, good. All right, so Miss Hanson, what two systems have we covered so far? What are their names?
The integrity system.
Integumentary system and the...
And skeletal.
And skeletal. Cool. And what's the integumentary system again?
Hair, skin, and nails.
Cool. And what's the skeletal system again?
Joints, bones, joints, and ligaments.
Very cool. Thank you. And why do I need an integumentary system?
To protect our insides, to protect us, to create heat, and to cool us down.
Yeah. And does it help me make vitamin D?
Yes.
And does it help me feel things?
Yes.
Awesome. And why do I need a skeletal system?
It protects our organs, it helps us move, and it produces our red blood cell, or our blood.
Yeah. Yeah. Thank you. Beautiful. All that's beautiful. Well done. Okay. Miss Nguyen. Miss? Yes. Miss Nguyen, what is the integumentary system?
bone, government, and joy.
I appreciate your paying attention, but listen to the question, because it's the question I asked you at the beginning of this entire thing. What is the integumentary system?
You say hair, skin, and nail.
Hair, skin, and nails. And what's the skeletal system?
Bone, government, and joy.
Yeah, bone, ligament, and joint. Good. Cool. Okay. Can we move on? Are we good?
Yeah.
Okay. Just want to make sure. Yeah. Okay. So today we're going to talk about a third system. This is the muscular system. Remember, we just created these systems to understand the human body because it's so complex. The muscular system can't exist without the skeletal system. In fact, the muscular system put together with the skeletal system is the reason I can do strange hand gestures. Right? The skeletal system is the levers. The muscular system pulls on levers. Right? Your book talks about the muscular system as though it's only talking about the skeletal part of the muscular system. It doesn't talk about cardiac and smooth muscle. Remember that there are 3 types of muscle? There are actually 3 types of muscle. One is skeletal, which is what we study in this class. The muscles that hook to my skeleton and help me move. But there's also my cardiac muscle, which is, what's the name for my cardiac muscle? No, what's the name of the thing that
Your heart?
My heart. Yes, that's my cardiac muscle. And then there's smooth muscle. Smooth muscle is wrapped around my arteries, my veins, most of my organs, all sorts of stuff. And it contracts too, but it's meant to open and close openings and things like that. We are just going to be talking about skeletal muscle because we care about movement and posture and things like that. And we're going to use all sorts of confusing terms. And most of those terms, to be very honest with you, I know for a fact most of those terms that you will forget later. And I don't really care because you won't use them every day. But I do want you to understand basically how a muscle functions because that will help you as a massage therapist. So before we go down this roller coaster ride of crazy verbiage and crazy names, I just want you to think for a second about how a muscle is formed. I want to just give you a big picture without lots of words. And then later we'll put the words into the big picture. Because otherwise we get lost in the words and we don't even know what we're talking about. We're just memorizing something, right? If you were to, I'm sorry, this is very graphic, but this is just the best description I can think of, all right? If you were to saw my thigh off right in the middle, you'd have a big thing like this, and you'd have a bone going through the center, because we cut it down like this. Does that make sense? Can we kind of see that? Okay, so, I mean, I would obviously bleed to death, and this would not be a real-life scenario, but the point is, if we sawed my leg down here, we'd have muscle around here and the femur right in the center of it, right? Yes. Okay. So essentially, you've got fascia around this entire muscle holding it together. Don't worry about the names right now. Even if you're taking notes, don't worry about them yet because I just want you to kind of have a big picture thing, right? And this fascia is called epimysium. And then you've got small bundles of muscle inside the muscle, and they're surrounded by fascia too. All this just helps keep your leg together. And that fascia is called perimysium. Doesn't matter, don't worry about the name. And then these bundles have smaller bundles in them. These are all muscle bundles, essentially. Not essentially, they are. And they're wrapped in something called endomysium. I always remember that one because it's end, it's the last one, right? And inside these bundles, these little bundles right here, are muscle cells. And muscle cells are very different from any cell in your body. Most cells in our body look like this, right? They're just a circle, right? Most cells in our body look like that. Muscle cells look more like that. They are long. Some of them run the length of your entire muscle. And they are skinny, 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 skinny. But they're still a cell. Right? They're a little bit unusual because anybody remember the powerhouse of a cell, the thing that makes energy?
Mitochondria.
Mitochondria. Thank you very much, Ms. Cooper. Mitochondria.
Mitochondria.
Mitochondria. Your muscle cells are a little bit unusual because they have multiple mitochondria. They've got multiple powerhouses because they have to produce a lot of power. Again, I'm not worried about the names yet. But here's what's interesting inside them. Inside them are these things that are filaments. And you've essentially got, I'm going to get rid of the mitochondria to make this thing bigger. In no way is this drawing accurate except to make this point, okay? like we'll see much better drawings in the book. I just want to kind of explain how a muscle contracts, can only pull. You've got these things, it's not even close to right. You've got these things called thin filaments, and you've got these things called thick filaments. And because of ATP in your body, which is the power that moves cells in your body and lets stuff move around, if you set these guys off, and you can set them off by putting some calcium ions in there, I'm going to go back over all this.
Wait, are we looking at a muscle cell or the mitochondria?
A muscle cell.
Oh, you're
Thank you for asking. A muscle cell. We're still in the muscle cell. I just made it bigger so we could see inside it. Inside that muscle cell are these filaments. And these filaments kind of have little hooks on them. And when they're activated, those hooks actually grab and pull on a microscopic level. And when they grab and pull, the muscle shortens. It comes together. So they literally go, and they shorten. And you've got a whole lot of sections of these. And all the sections can grab and pull. And if a whole bunch of sections grab and pull, the whole muscle comes together. Because all these sections go, and they all grab and pull. And they're actually quite strong even though they're microscopic. And that's essentially how your muscle contracts. And then if they let go, your muscle lets go. They can only really grab and pull, right? That's why your muscle can only contract. But it's these little filaments that actually grab and pull. That's why the muscle kind of balls up, because they kind of pull themselves over each other, kind of. That's what's going on inside these really long cells. They've got these small filaments that can grab and pull each other and come together and contract. And I just wanted that kind of conceptual understanding before we learn a whole lot of names for what that is called. Because ultimately, the names don't matter. If we called massage class peanut butter class, it would still be massage class, right? We decide on that kind of stuff. The names is what gets kind of confusing with some of this stuff. But I just want you to understand, once again, muscles can only contract. Yeah? That's all they can do. And it's because these microfilaments can pull. That's all they can do. And they pull based on the amount of energy available and all that kind of stuff. Yeah?
Does it matter what the thick or thin filaments do? I mean, as far as for us to understand?
It does, and we're actually going to talk about them. Yeah.
Okay.
I just want to kind of give you an overview that there's these things that kind of, and that's what really causes the muscle to come together. Because they're going to tell you all these names around that in a second. Here's the other interesting thing. This muscle cell can only contract or not contract. It can't kind of contract. So this muscle cell either gives us 100% of its effort, 0% of its effort, or 100% of its effort. Unlike us, it's either full on or full off. So the way my body regulates power, obviously I don't need, even though I'm out of shape, I don't need all my strength to hold this pen up, right? And there's a reason I'm not lifting it up still. It's because I'm not using all my power. What my body does to do something like this is it only activates, say, 10 cells. It just says, let's activate 10 cells, all at 100%, but they're all just lifting this thing. Now I've got to activate 100 cells, right? Now I've got to activate 1,000. And you've got hundreds of thousands. So your body really just turns them on or off. The muscles either go all out or not. Muscle cells either go all out or not. And your body just chooses to turn on some cells or not. It's very intelligent. So it'd be kind of like we're all playing tug of war, right? And first I'm just the only guy holding the rope. And I'm like, well, that's not enough. Miss Petrie, come over here. And now we got her because we got more things to tug. But we're all tugging as hard as we can whenever we're used. Miss Nguyen, come here. And she starts tugging, right? When we need more power, we recruit more muscle cells. Your body does. It turns more on. But the muscle cells are either on or off. They don't know how to do kind of. They're either like, yes, you turned me on, I'm going to pull, or no, you didn't turn me on, I'm going to sit here. That's it. And so your body controls your strength by how many muscle cells it activates. That's it. It's very complex, actually. Your brain is all doing this in the background. You don't have to think about it. Okay. Don't worry about all that. We're now going to start back all at the beginning with a slide presentation and talk about the muscle system, and we will come back to this point later, and we'll put words around it, and we'll discuss it more in more depth. But I just wanted you to kind of have an overview, because I think it's kind of confusing otherwise. Yeah? So let's go back. Let me share my screen with you guys. Okay. So, hopefully, you can see the screen. Muscular system and pathologies. Yeah. What does pathology mean?
Study of disease.
Thank you very much, sir. Study of disease. Yep. Awesome. Okay. Chapter 20. Your skeletal system, I'm sorry, so sorry. I just saw skeletal up there, it threw me off. Your muscular system is composed of your skeletal muscles, your smooth muscles, and your cardiac muscles. Again, your book doesn't really talk about the smooth and the cardiac, and I'm okay with that because you're not going to massage the smooth or the cardiac. However, what is CPR? Anybody know? Anybody CPR certified? Anybody? Thank you, Ms. Shawness. What are you doing in CPR to save somebody's life?
You're like doing the pumping.
Yeah.
That's hard with pumping.
Yes, you are pushing the chest down to massage the heart to keep it pumping. You are literally trying to squeeze the heart. In fact, if a surgeon was there and your chest was open, they reach in and grab the heart and they pump it. They massage it. So CPR is a form of massaging the heart. But anyway, we're not going to be doing that in our massage. So, and the smooth muscle is the stuff around the organs and tubes. All we're going to be talking about today is skeletal muscle. So that's it. That's the main thing we're talking about. And skeletal muscle is any muscle that attaches to your skeleton. So this is the muscle that helps you have posture and helps you to move. Yeah? Yeah. Okay. So skeletal muscle, tendons. What do tendons do?
They attach muscle to bone.
You are absolutely right. Miss Petrie, what do tendons do?
Attach muscle to bone.
Thank you. Miss Belodic, what do muscles do? I mean, what? What do tendons do?
They attach muscle to bone.
Cool. Miss Harper, what do tendons do?
Attach muscle to bone.
Thank you. All right. I'm running that in the ground, by the way, because it's like Massage 101. You just have to know it. All right, cool. So let's look at skeletal muscles, right? By the way, the things I underlined in this slide are what your book considers the muscular system to be. I threw in smooth and cardiac because they're part of the muscular system, but your book's not discussing them because they're not massage related, which is fine by me. I'm fine with that. But I underline the stuff that your book's going to kind of consider important in this case. Okay, let's talk about what the muscular system does for me and for you. And does it ask for anything? No, it just does it. Yeah. Movement. Movement. The study of movement is kinesiology. All these actions you're learning actions so you can explain why I can do this. Yeah? We are explaining those kind of things. That is movement, and your muscles do that by pulling on bones. So we have to put two systems together to get movement, right? Two systems in your body to get movement. Miss Monreal, what two systems do we have to put together to get movement?
Skeletal and muscle.
Yeah, skeletal is the levers and the muscle is the power. Thank you. Thank you. The other thing that my muscular system does for me is gives me posture. Right now, hundreds of muscles are turning on and off so that I can stand here in front of you. I'm doing it quite well, I'd like to say. I don't want to brag. But the fact is, right now they're pulling me a little bit this way, pulling me a little bit that way, pulling me a little bit this way, pulling me a little bit that way. They're holding me upright. They are creating my posture by firing just a few fibers all over the place. And that's muscle tone. Muscle tone is what gives me posture. Some people call it tonus. It's when my muscles right now, like in my back, are just some of the strands are firing to keep me upright, to give me posture. Yeah? In fact, guess what my body does? It's so smart. I've got these muscle fibers in my back, right? I've actually got hundreds of thousands of them, so this is not a very good example. But it'll fire these two for a little while. Guess what? These two get tired. So it stops firing them and it'll fire the next two for a while. And they get tired and it'll fire the next two for a while and go back around. It's doing that all automatically. I don't have to think about that. It's like we just need a couple fibers working so it'll fire, but then they get tired. So it's like, well, we'll use these fibers too. It'll switch around inside the muscle. It's kind of cool. The other thing muscles do is help produce heat. Muscles produce heat. Have you noticed how in general, but not always, in general, men are always warmer than women? That is not a sexist remark. It's a remark because in general, men have more muscle mass and more mass to begin with too. Both those things. Because what holds my heat in? What system of my body holds my heat in?
The integumentary system.
Yes, ma'am. You are exactly right. Thank you very much. So, if I've got thicker skin than you, because it's got more adipose tissue, which is my nice way of saying I'm fat, if I have more adipose tissue in my integumentary system, I've got better insulation, and if I've got more muscle inside producing heat, I'm going to feel hotter all the time, right? So, it also does produce heat, and you need heat, by the way. If your core temperature drops more than a few degrees, your core temperature where all your organs are, you're a goner. Your arms and legs can get really, really cold, but your core temperature has to stay around 90, 98 or whatever it is. Yes, ma'am.
Is that why men can have a higher caloric intake because of just even resting? They need more because they have more muscle mass?
Yes. So it's an advantage to anybody with more muscle mass, but you're right, it generally is men.
Okay.
Because their muscles are actually burning the caloric mass off that they just ate. Yeah. Anybody ever heard of the meat sweats?
No.
No? It's kind of gross, but if you eat a whole bunch of meat, a whole bunch of calories, one of the things your body tries to do to regulate your weight is it tries to burn off some of that by producing heat. You've got some fat cells that actually try to burn off some of those calories because your body's like, we do not need this much calorie right now. And it will actually try to, so you get kind of hot and sweaty. You ever eat such a big meal you're kind of hot and sweaty? Yeah.
Now, what if you've been like working out really hard? You know, you're doing a diet where you require 3,000 calories a day, and like, does it still happen?
No. If your body really does this, if your body really does feel like it's in a deficit, it will try to consume those calories.
Okay.
Yeah. But remember that your body's not thinking ahead in that sense, so it would probably be good to space out those 3,000 calories throughout the day.
Oh yeah, no, just all at once. Like,
Yeah, all at once your body's just going to be like, I don't know what to do with 3,000 calories at once. It's kind of like my car and gas. I can fill up the tank, but it doesn't use it all at once, right?
Okay, yeah, so like, okay, that makes sense.
That's why they make the big deal about lots and lots of small meals. Yeah. But you're absolutely right. Bodybuilders try to make sure they're never hungry. Yeah. Okay. So movement, posture, heat production. That's good stuff. Okay. So, before I start explaining this, muscle cells have all the features that other cells have. They've got some new stuff, newfangled stuff in them too. But a muscle cell is a cell. It's a cell like a skin cell or like anything else. It's got, a nucleus, and it's got cytoplasm, that goo inside, and it's got a cell membrane, and it's a cell. But because anatomy people like to make stuff really, really difficult, they call most things that are related to muscles and muscle cells have the word sarco in them. Sarco is Latin for flesh. And by flesh they mean muscle. So we take all the normal cell stuff and we change the names and we put sarco in it. Right? So when we're referring to muscle cells, that is, we put the word sarco in it, and it just makes things confusing. I'm trying to explain to you why sarco is in a lot of these names instead of just calling them stuff. So remember we had cytoplasm. Cytoplasm was the goo inside a cell. I hope you guys remember this. Cytoplasm was the goo inside a cell. Well, muscles have the exact same stuff, but will they call it cytoplasm? By the way, cyto means cell, so cell plasm. No, they call it sarcoplasm. I don't know why. Drives me nuts. So I'm making this whole speech about this right now because this is part of what's confusing about this chapter and about understanding this stuff. When you walk away from these 2 days, I want you just to remember the big picture stuff, right? I don't care, actually, to be very honest with you, if you remember it's called sarcoplasm or cytoplasm. I just want you to remember it's still a muscle cell, it's still a cell, and it has some of those properties of cells and such. So I'm just trying to explain to you. Okay. So there's a muscle fiber, and a muscle fiber is a muscle cell. So why do they call it a muscle fiber? Remember, most of our cells look like this. Your skin cells and stuff, most of them are round. That's not completely true. There's some kind of flatter ones and things like that, but close enough, right? And then comes your muscle cell. And it's like that. Well, on a microscopic level, that looks a lot like a fiber. So a muscle cell is called a muscle fiber because it is a fiber. Does that make sense? But it's a living fiber, it's a cell. They're the same thing. It's just a very long cell. Cool? All right. It is full of like sarcoplasm, which is really cytoplasm, which is the intracellular fluid that all cells have. Yes. And inside it are these myofibrils. Myo means muscle and fibrils are fiber. So inside here are those long strands I talked to you about. Those long strands inside. These are the long strands that essentially crawl over each other. Yeah.
I just have a question. So is the, and I don't know if I'm jumping ahead, but is the cytoplasm inside that long cell?
Yes. Yeah, it's a cell. It's just a
Okay.
cell that got stretched out, but the cytoplasm is inside the cell. It's intracellular fluid. It's cytoplasm. I don't really know why they call it sarcoplasm. It's cytoplasm in a muscle cell, so it's sarcoplasm, but it's cytoplasm. Yeah. It does have some slightly different properties because muscles need slightly different things, but it's the goo inside the cell. So
But then the little myofibr whatever,
Yeah.
that's in there too?
That's in there too. This is what's going to help the cell contract.
Okay.
So, I'm going to draw this muscle cell bigger so I can make some examples on the inside. So this is not a very accurate shape, but I want to make a really long muscle cell or muscle fiber, right? It's got these little filaments on the inside that actually pull over each other. These are the things that grab on each other and pull, all right? But they do it in sections. They're microscopic. They can only pull a little bit. So you've got these little sections. These little sections that are called a sarcomere. And it's hard to imagine, but this little sarcomere here, that little one does this. And the other sarcomere does this, and the other sarcomere does that. And if you have a big long cell, and this sarcomere goes deep, and this one goes deep, and this one goes deep, and this one goes deep, I don't think they actually make that noise. Deep, deep, deep. The whole muscle cell goes doof. Yeah? If they all move a millimeter and you've got hundreds of them in there in this long chain, boom, the thing shortens. So I tried to put an example in here. I think it's a terrible one, but it's the best thing I come up with. This is your train. These are the cars on the train. The sarcomeres are the cars on the train. If you made all the cars shorter, the train would get, even if you just took a foot off every train car, the train would get a lot shorter. That's how contraction occurs. These micro fibrils crawl over each other at each of these little junctions. And these junctions, these little areas are called sarcomeres. That's where the contraction occurs inside the cell. And you've got this big long train of sarcomeres with these filaments inside that go doot, and pull over one another. And actually, if I stopped right there, that would be about the clearest explanation I could give to just basically how a muscle works. And probably the most important part to know. That basic concept of what's going on inside there. Okay. So there's some stuff in my notes here. I actually made these like zigzag because these are called Z lines between them. And that's what connects them, right? And all these fibers, by the way, make your muscle look striped. And so they call skeletal muscle striated muscle. It's striped muscle. Smooth muscle is not striated. This stuff is striated. It's made especially for this type of work because it looks striped, so they call it striated. We'll probably get to that here in a second. Here's a picture from your book, and it's good. It's just very hard to kind of see, but I'm hoping that we gave you backstory to this so that we could kind of look at this whole thing. And here I think you can see the entire muscle is covered in fascia. There's this epimysium around it. Then there's smaller bundles that have perimysium around them. Then even smaller bundles that have endomysium around them. And these are all just fascia. Just plastic wrap around, plastic wrap around, plastic wrap. Just like cables, just like wiring. If you've ever seen a really big wiring into a house or something, it's got all these small bundles of wire in there. And all the wires are wrapped in plastic, then groups of wires are wrapped in plastic, and then all the wire is wrapped in plastic, right? Your muscles are exactly the same way, but the plastic's called fascia. So you got fascia around the whole muscle. Really, this is superficial fascia, actually, around the whole muscle. But anyway, then epimysium, then perimysium, then endomysium, and then you got the individual muscle cells, and they're long, right? And those are filled with these filaments, these thin and thick filaments that we're about to talk about. But the whole purpose of the thick and thin filaments is these are the things that go doop, doop, and pull over each other. So you got a muscle, you got a whole bunch of muscles actually. Epimysium, smaller groups of muscles, perimysium, smaller muscle fibers than that, endomysium. Individual muscle cells are muscle fibers. Muscle cells, muscle fibers, same thing. And those are filled with the thick and thin filaments that crawl over each other in little groups of these little sarcomere groups. Yeah? Oh, I think I went the wrong way. Does that kind of make sense? Does me even asking if that kind of makes sense help? Kind of, sort of. Yeah, yeah. Let me go backwards. Let me go backwards. I'm God or Mother Nature or something. I don't think I'm either one of those things. I'm just trying to say, like, I'm trying to create something that pulls because I want to make human beings be able to move their bodies and animals, by the way, and all sorts of stuff. Anyway, so I get these filaments that will actually kind of reach out and pull each other together. And I put them in a little unit. They can only pull a little bit. They can only go from like here to there. And that's a sarcomere. I take this little unit. We're going backwards. We're going to build up the muscle now. I'm like, well, this can only pull a little bit, and I need this muscle to move like a lot. So I'm going to put another sarcomere here. And another sarcomere here. And another sarcomere here. Another sarcomere here. And then I'm like, that's kind of cool, because now they go deet, 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 deet. The whole chain kind of comes together. Right? And I'm like, well, I got to feed these things. So I'm going to put them inside a muscle cell. So they've got sarcoplasm around them, things like that, so they can, I mean, it's living stuff. It's got to be able to live and repair and all that kind of stuff. So I put all these little sarcomeres inside a muscle cell. The muscle cell's so long that it's a muscle fiber. I mean, it really is a fiber. It's so long and thin. It's a muscle fiber, but a muscle fiber is a muscle cell. And I'm like, that's cool. And when I turn this thing on, it gives me 100% effort. And I'm like, well, that's great. But for one thing, just one of these isn't strong enough really to do anything. In fact, guess how many of these I need to lift up my eyelids? Any guesses? How many muscle fibers you need to lift up your eyelids?
1 million. Just kidding.
I wouldn't necessarily be wrong. It's 10. But think how light my eyelids are. I mean, I know your guys' eyelids feel heavy in the morning when you're listening to me, but they're not that heavy, right? Now, it does, by the way. Miss Monreal's not wrong, by the way. You use 1 million, like, to do lots of things, like squats. You're easily using 1 million fibers. So that's not an unusual number. But for your eyelids, it takes about 10 fibers to lift them up. So I say, well, I've got to create 10 of these cells, right? So I create 10 of these cells. I realize that's not 10. And muscle fiber, by the way, even though it's really good at pulling, it's very soft. And so I better wrap this stuff in something to protect it. I'm going to wrap it in fascia. So I wrap this whole thing in endomysium. It just makes it stronger. I just kind of protect it. I'm like, well, that's really cool. And that's great if I want to lift up an eyelid, but what if I want to lift up a coffee mug? Well, I'm going to need big groups of this together. So I'm going to make another one of these bundles. I'm going to get another endomysium bundle. And then once I get a whole bunch of those, I'm like, well, I better wrap these in fascia. So I wrap them in paramycium. Then I get a whole bunch of paramycium bundles and I wrap them in epimycium to make up a full muscle. So like one electrical wire, which is nothing like muscle, but it looks like it. One electrical wire is just like a muscle fiber, right? You get a whole bunch together, you wrap them in endomysium, you get a whole bunch of those bundles together and you wrap them in paramycium, and then you get a couple big bundles together and you wrap them in epimycium, because you got to wrap everything in fascia because muscle's very tender. When you're eating filet mignon, it's got very little fascia in it. That's why it's very tender, and that's why it tears easily. And when you're eating tougher, stronger muscle, it's got more epimycium, endomycium, paramycium in it. Okay. That was backwards and forwards. Questions so far? Okay. All right. Okay. So, remember the sarcomeres are these little train cars that are the part that actually contract inside the muscle cell. And inside them, I told you there is these thick and thin filaments. That's what actually allows them to contract. Yep. And they're stacked in this very honeycomb-like way that makes them look striped. And that's why they call your muscle striated. And that's actually important. It's important because they refer to skeletal muscle as striated muscle. So you need to know the term. It just means striped. Your smooth muscle is not striated muscle. Your skeletal muscle is striated muscle. But the thick and thin strands are the microfilaments. They're the things I already told you about inside these little sarcomeres that pull together. They create these little contraction units. They're missing one here. Okay. So. Oh my gosh. So bear with me. So we're going to come down through a muscle again. We're going to start with a big muscle. We're going to tear it down and get to a very small thing and talk about these filaments. So, I first need to take off the top layer of fascia that is found around the entire muscle. And the top layer of fascia is what? What's it called?
Epimysium?
Epimysium, epimysium, both are correct. Thank you. Epimysium, we'll take it. Thank you very much. Miss Felix Osuna. What's the top layer of fascia called that we're going to remove around this whole muscle?
I was in the bathroom.
Oh, all right, that's okay. Wait 1 second. Miss Monreal, what's the top layer of fascia called that we're going to remove?
Epimysium?
Epimysium.
I forgot, what was the other way you said it?
Epimysium.
Epimysium, okay.
Yeah, I think of myo. Myo means muscle, so epimysium. I mean, I don't know. I don't know if I'm right, to be honest with you. Epimysium we'll take. Epimysium. Miss Felix Osuna, what's the top layer of fascia we're going to remove from the muscle? Epimysium. Thank you. Miss Bolotic, what's the top layer of fascia we're going to remove from around the muscle?
Epimysium.
Awesome. Thank you very much. Then I'm going to go down the next layer. I'm going to get rid of that fascia, get us down to a smaller bundle. That's wrapped in fascia too. What's that called? It starts with a P, somebody else.
Paramecium?
Excellent, and thank you. I'm thanking you for being brave enough to, possibly say the wrong answer, right? But you're right, paramecium. Paramecium. So, Miss Torres, what's the next layer of fascia called?
Paramecium.
Thank you. So the
Paramecium?
paramecium, we'll take either one. I don't mean to confuse you guys, but I say paramecium because I think of myotherapy. My means muscle. Paramecium. So we started with what, Miss Torres? What was the first layer? The outer layer?
Sorry, just thinking a little bit. Epimysium?
Epimysium. Then we went down to what?
Paramecium?
Yes, and at the end, we got to what?
Endomysium.
Endomysium. Thank you. By the way, around this entire muscle, there might be superficial fascia and all sorts of stuff.
I'm sorry, I think I'm a little lost. Is that a cell? Is that what we're...
No, and thank you, Miss Petrie. Thank you for asking, because yes, we would have made it worse. We are talking about like a thigh right now.
Okay.
So, in reality, by the way, your thigh is probably wrapped with superficial fascia, but then you've got epimysium, paramysium, endomysium. We still have to get down a little smaller to get to the cell, really. So, yeah, go ahead.
Of what then?
What?
It's each layer of what then?
Fascia. And what you guys can honestly think of it as, although it's living and breathing and it's amazing, but it looks a lot like saran wrap. So we got saran wrap around the whole muscle. And what do we call that, Miss Hunter, the saran wrap that's around the whole muscle?
Saran wrap, is it, it's not, is it the first layer?
Yeah.
It's epimysium.
Beautiful. Epimysium, then I go down a layer and that's what?
Paramecium.
Yep, then I go down a layer and we get to the end and that's what?
Endomysium.
Good. And then I get to the muscle fiber, which is just the muscle cell.
Oh, am I supposed to answer that? I don't know.
Well, I wasn't sure the question was clear enough, so I went ahead and answered it. I was like, I don't know if she'll know what I'm asking. The muscle fiber. So now, Miss Petrie, now we're down to the muscle cell, which we call muscle fiber. And inside that cell are these little contracting units called sarcomeres. Contracting units called a sarcomere. And they're all hooked together by these Z lines, right? And they've got thin and thick filaments that help them pull together because the thick and thin filaments pull themselves over each other. And these thick and thin filaments are made with protein. Anybody ever tell you you got to eat protein so you build muscle?
Okay, hold on, I wanna try to remember. Okay, so the filament, inside the filament is the Z things, right?
The Z things actually have filaments running between them.
Okay. Oh, this is so confusing.
It
Okay.
is. It is. So it is confusing.
Okay, what makes up the filament?
Protein.
Protein.
We're getting to that right now.
Okay.
It is confusing. We've got multiple muscles together wrapped in this fascia called epimysium. Then maybe singular muscles kind of, this isn't exactly right, but I'm just trying to give you a visual here, paramysium. Then little muscle fibers wrapped in endomysium. Then if we look at a long muscular cell, we call it a muscle fiber. Inside that muscle cell are a whole bunch of sarcomeres. They're all separated by this little Z line, but they're hooked together like train cars. And those sarcomeres that are inside the long muscle cell, there's a whole bunch of them. Every one of those sarcomeres has little fibers inside it that can do this. That's literally what they can do. Little sarcomeres like this, they got quite a few fibers, but they go, and that's how the sarcomere goes like this. And the muscle cell's got a whole bunch of sarcomeres going, and the whole muscle cell goes and pulls together. Does that help?
Yeah, I guess I'm just trying to figure it out, kind of how you started out the lesson as far as like, okay, the cell makes up this and this, and so I'm just having like trouble with the progression. So just never mind, it's okay because I'll just watch it again later.
Okay. I don't mind the questions because I'm looking across the audience here right now, and I do not see any like, yes, I've got this kind of stuff.
Okay.
And I read the book
No.
too, and I was like, oh man, I don't think the book does a very good job with this.
I'm also being distracted by the picture or not the picture, the page you have there. So the thin myofilament, that goes back to where it's thick and thin. Those little tubes that said thick and thin, right?
That are in the sarcomeres, that are all chained together, that are inside a muscle cell. A whole bunch of muscle cells are wrapped in fascia. Those groups are wrapped in fascia. Those groups are wrapped in more fascia.
Okay, so the myofilament is inside a sarcomere.
Yes! Quite a lot of them.
Okay.
And their job, on the most basic level, the job of the thick and thin filaments is to grab, well, the thick one to grab and pull each other together so the sarcomere gets shorter.
Okay.
But it's microscopic. These are like little molecules. It's microscopic. So this thing getting shorter doesn't do a lot. But if you got a whole bunch of them getting shorter, the cell gets shorter and the muscle contracts.
Okay. I think I'm having a better idea. I was like, okay, is a myofilament in a sarcomere? Is a sarcomere inside the myofilament? So just, I'm trying to see what the progression is.
Yeah. Microfilaments, thin and thick. Microfilaments are thin and thick, and they're inside the sarcomere, and there's a whole bunch of sarcomeres lined up like a train inside a muscle fiber or a muscle cell. Yeah. And then we start wrapping all those cells in fascia and groups of those cells together in fascia to make up a muscle. Yeah. So, I don't want you to get too caught up in about how thick and thin filaments work, because if you think your head hurts now, it'll hurt even more. I'm not just talking to you, I'm talking to all of us. It'll hurt even more. And there's some stuff you don't need to know if you're not, going to pursue advanced biology of muscular action. But actin is the main protein in thin filaments. Actin is the main protein in thin filaments. And myosin is the main protein in thick filaments. The fact that your filaments, by the way, are made up of protein is very significant, because that's why you need protein to make muscle. Again, this thick and thin filaments, these are the guys that grab each other. The main protein in thin is actin. and myosin is the main one in the thick ones. By the way, actin is a shorter word. It has one less letter than myosin, and thin has one less letter than thick. So actin is a thinner word than myosin, or myosin is a thicker word than actin. It's just a good way to keep them separate if you want. So if you're like, I don't remember if it's actin or myosin that's in the thick or the thin, well, the longer word goes with the other longer word. That's just a trick to remember them. I'm only even telling you this level of detail because people do sometimes refer to this in medical literature and things like this. So your thick filaments are mostly myosin. They're mostly made out of this protein. And essentially, the thick filaments are essentially in the center of these bundles. The thin filaments are out here. And it's the thick ones kind of grab on and pull through. Let's see if we have a picture here. Yeah, this one's not going to help you a lot. Let's see. Hold on, everybody. I don't even like this one exactly. Don't worry, by the way, please don't worry about I bands, H zones, Z lines, all this stuff. Z lines just separate the railroad cars, the sarcomeres, but don't worry about I bands and H zones. It has to do with chemically how this works, and we don't want to get into that. Okay, so let's go back one actually. Can you guys see the blue lines here? Okay. So let me draw this on the board really fast because I don't think they have the slide. So the blue line, let's say we got a blue line kind of shaped like this, right? What's the other color? Pink? I got a red here. This is made out of myosin, it's your thick line. This is made out of actin, it's your thin line. I hope you can see this because when I release calcium ions into this, and there's a way to release calcium ions we'll talk about, but when I release calcium ions onto this, a chemical reaction happens, and these little guys flip. And so you've got, so instead of going this way, they all go this way. If this is a thin filament of actin and this is a thick filament of myosin and this flips, it contracts. It pulls itself along. It pulls the thin filament this way. That's exactly what happens. It mechanically actually flips and those little molecules grab on here and it actually pulls. That's how it works. These things are going this way and they flip back and pull the muscle along. That's what the thin and thick filaments do. The thick actually grab onto the thin. The thin, by the way, have all these bumps on them. Doesn't matter. It actually grabs onto those bumps and those arms flip and the filaments get closer together and that sarcomere shortens. And when that happens in an entire muscle cell, because you release calcium ions throughout the entire muscle cell, all the sarcomeres shorten and the muscle contracts and I'm able to do stuff like this. Although that might have taken multiple muscle cells, but the point is, that's how that happened, literally. Miss Monreal? I'm just using you as my barometer, I guess, right now. So, does that kind of make sense? What are you thinking? What are your thoughts?
It does. I mean, it does. I just have to like go over it a few times. That's why I'm gonna watch the video again when I come home.
Sure.
Like it's fine because it's gonna like kind of percolate and just
Sure.
marinate in my head for a little bit.
Totally cool. Got it. And by the way, I apologize to all of you. There's this sense of scale that's hard too, right? We start with this whole leg, and I'm like, it's wrapped in fascia. But then we get down the cell, and I'm like, that's still not small enough. Inside the cell are these little railroad cars, these sarcomeres. Inside them, there's these tiny little microfilaments, and then the thick ones grab the small ones and pull them together. The best I can hope for, and all I actually hope for, is that you kind of visualize that eventually, everybody. And you kind of get this concept. What?
Well, sometimes I get worried, not worried, that's too strong of a word, but when I'm like trying to retain everything, and I appreciate when you say, okay, you won't need this. So I'm like trying to soak it as much as I can, and sometimes we get to the test and I'm like, okay, I didn't even need to worry about that other stuff.
Yeah.
So a lot of times I'm kind of just like on guard a little bit, trying to say, okay, pay attention to this, pay attention to this.
Yeah, which is
So
why...
I'm a little overwhelmed.
Yes, I don't blame you. Which is why I also said stuff like, don't worry about the I bands, don't worry about the H zones. Like, it won't serve you in your career, and you're just memorizing useless information. And it's why when I go back and repeat stuff with you guys, it's the stuff that I think you're going to need to know long time from now, which is endomysium, paramysium, epimysium, muscle fiber or muscle cell, little sarcomeres inside it, microfilaments inside the sarcomeres, thick pulls the thin, actin and myosin. That's it. That's all I think we should remember from this. I know I said it really fast.
I know why you just did that, because that's exactly what put the progression in my head.
Yes.
That's what I needed.
Yes.
Okay.
Cool. All right. And by the way, you know me, it won't be the last time we talk about it. But yes, we want a conceptual understanding. Yeah. Basically, there's tiny little hairs that pull over each other, and you get a whole lot of groups of those, and then the whole muscle contracts. All right. Let's move right along. So I said that the way we get this thing to activate, the way we get these myosin strands to pull the actin strands, the way we get these thick strands to pull the thin strands along, is we have to activate a chemical reaction in them. This requires ATP and all that stuff, but the way we activate, and ATP, by the way, is the energy your body uses, but the way we activate this is we have these tubes that are called sarcoplasmic reticulum. I'm so sorry for that word. It's endoplasmic reticulum in regular cells, but since it's a muscle cell, they call it sarcoplasmic reticulum, but they're just tubes. They're just tubes that can store and release the calcium ions. And so they dump the calcium ions in the cell, and it tells these fibers to activate and pull. And when they're done pulling, those tubes take back up the calcium ions, and they stop telling them that. So
the calcium ion is like a note, like I'm passing you a note.
Sure. Yes. Yes, it's a catalyst, but yes, it's a note. It's me passing you a note that says, hey, pull this, and when you're done, give me back the note. And so you give it back to me, and you stop pulling it. And the next time I want you to pull again, I give you the note again. And then when you're done, you give me the note back. Yeah, it's kind of the, I don't know if it's switch. It's the chemical switch. And when they're done with it, they give back the chemical switch. Yeah. Yep. Because something has to set off the chemical reaction. And calcium ions tell it to do that. Yeah. Cool. So really just remember that sarcoplasmic reticulum are the tubes that hold the calcium ions that tell your body to turn on and off these reactions of the thick myosin fibers pulling the thin actin fibers that are in the sarcomeres, that are in the muscle cell, that are wrapped in fascia. Anybody hate me yet? No? Good. Okay. Well, we're not done. So I don't actually want to go over this because I think it'll confuse things more. Boom. Okay, and I might want to stop here. Bear with me 1 second, everybody. Oh, I do. Perfect. Okay, let's take a break. So, thank you actually, Miss Monreal, because you kind of helped kind of sum up things for us. And so I want to give us a big analogy based on what you just said because it kind of helped me. Okay? I want to use the choo-choo train analogy. Okay? And before I do that, can we all see that if I make a train out of these pens, it's going to be a certain length long, and that if I make a train out of shorter pens, that train is not going to be as long, right? Okay. Can you see that, Miss Stanley? Was that a yes or was that a no? I can't see there. Or no, it's not going to be as long.
I was responding to no, it's not going to be as long.
Cool.
Here and there you can see, but most of the time you're frozen.
Oh, understood. Okay, cool. All right. Not cool, but I get it. Thank you. All right. We have a train. I'm going to try to make it even bigger because I want to make sure you guys can see back there. A train. These are the train cars. There's 1,000 of them, but I ran out of whiteboard, so I can only show you 3. But there's 1,000 of these cars, these train cars. All of them put together is a train, right? We're going to call our train a muscle cell. The whole train is a cell. The train is so long, this train is so long, we can also call it a fiber. Because seen from far away, that 1,000-car train looks like a fiber. Really far away, you're up in a spaceship, it looks like a fiber. It's a cell. The train is a cell. Right? And that cell is made up of 1,000 cars. The cars are connected by the thing in your book that's called a Z-line. We don't even care what a Z-line is, it just connects the cars together. That's it, we don't even care. Each car, our train's kind of weird, so we call our cars, our train cars, our box cars, we call them sarcomeres. Here's a sarcomere. Here's a sarcomere. Train cars, they're sarcomeres. We got 1,000 of them. These are very weird train cars. Inside, they've got these thin filaments and these thick filaments. They're made out of actin and myosin. It doesn't really matter. It's just this weird stuff. Who knows? I don't know. You get it when you eat protein. These train cars are made out of these thin fibers. And these thin fibers can actually grab each other. If you dump calcium in here, calcium ions, for some weird reason, a chemical reaction happens, and inside the train car, the fibers pull the car together. And the car gets a little shorter. Not a lot, but a little bit on a very microscopic level. But there's 1,000 getting shorter. If my train gets 1 inch, if each car gets 1 inch shorter, but there's 1,000 of them, my train got 1,000 inches shorter. That's a lot. So the whole train contracts, or the muscle cell contracts, or the muscle fiber contracts, because all the little sarcomeres, the train cars, contracted. Does that make sense? Cool. Now, I find it very convenient that this train contracts. And all it can do is either contract or not. It gives me 100% power. If I need more power, I need a whole nother train. If I need more power, I need a whole nother train. Whole power, I need a whole nother train. To keep all those trains together, I wrap them in fascia. If I get another group like that, I wrap the 3 groups or the 4 groups together in more fascia. I get more groups like that, I wrap them all together in fascia, and by now I've got a leg. Does that kind of help you settle stuff in here? Good, good, I saw a couple nods. We'll take it. Cool. So we've been talking about the microscopic stuff. I mean, I realize we just got up to a whole leg, but the sarcomeres, You're never going to see a sarcomere in your life. You're never going to see a muscle cell in your life, probably. We deal with lots and lots and lots, and by the way, by lots and lots, I mean millions of muscle fibers at once. Millions and millions of muscle fibers at once to make up a muscle. So that was microscopic, tiny stuff about why can your muscle contract. And basically contract because actin and myosin strands grab each other when calcium comes through these tubes in there and kind of tells it to contract. And of course you have to have ATP available, energy available in your body to do this, but that's what happens. And then a whole bunch of them together contract a muscle. Now we're going to go a little bit bigger picture. Okay? We've already talked about the 3 layers here of connective tissue. We talked about the epimysium that surrounds a muscle. Perimysium surrounds these things called fascicles, but fascicles are just bundles of muscle fiber. And then endomysium, which wraps around individual fibers. And all of this is just to protect your muscle fiber. Muscle fiber needs a lot of protection. So remember, it's wires wrapped around more, wrapped around more, wrapped around more stuff. Yeah? And you should know what epimysium, perimysium, and endomysium is, because fascia is a big deal to massage therapists. And a lot of times when you're massaging somebody and you think you're massaging their muscles, you're actually massaging their epimysium, perimysium, endomysium. Not directly, but to get it to stretch out, because it too can shorten. So you're trying to open that stuff too, right? Okay. I thought somebody was going to say something. Okay. So your muscles, your book likes to say your muscles is groups of these I'm trying to think of an easier way to say this. Your muscles are just bundles of muscle fiber. Your muscles are just a whole bunch of muscle fiber. They really are. What do tendons do? Who can tell me what tendons do?
They attach muscle to bone.
They attach muscle to bone. Why do we want to attach muscle to bone?
Because the bone is like the lever.
That was exactly the answer I wanted. The bone is the lever, the muscle attaches to it, and if the muscle contracts because of thousands of sarcomeres contracting in thousands of muscle fibers, and it shortens, the lever will move. And when the lever moves, I'm moving. Yeah? Cool. Aponeuroses and retinacula. Aponeuroses and retinacula and tendons are not muscle fiber, they're fascia. But we include them in the muscular system because they have a lot to do with the muscular system, right? Epimysium, endomysium, perimysium, tendons, aponeuroses, retinacula are all fascia. So hold on because this will help. Hold on. Let me grab something really quickly. All right, here we go. All right, everybody, can we all see this? Boom. Miss Felix Osuna, what am I holding?
Fascia?
Yeah, that's actually a great answer. Cool. Miss Harper, what am I holding?
It's plastic wrap.
It is plastic wrap. So it's plastic wrap, but I like what you said because that's what I was expecting. And Miss Felix Osuna is right. I'm going to use this to explain fascia. Miss Bilotic, what am I holding?
Fascia.
Cool. Either answer would have been fine. Honestly, fascia looks like this in your body. If you've ever prepared chicken and stuff, and you've taken like a thin coating off a chicken breast or something, and you can basically see through it, but it's really tough. That's fascia. Cool? All right. So let's look at this in a lot of different ways. The fascia wrapped around an entire muscle. An entire muscle is epimysium, right? But inside this entire muscle is tinier muscles, groups of muscles wrapped in fascia. And inside that is little tiny fibers wrapped in endomysium, which is also fascia. So let's pretend this is not going to be a great example, but bear with me. We'll try to make this work. Give you an idea. Hang on. It'll be worth it. Just from the visual, it'll be worth it. All right. Almost there. One more. Okay. And, all right, everybody. Pay attention. Because this fascia has everything to do with massage therapy. Fascial health, changing fascia, stretching fascia, working with fascia is everything about being a massage therapist. We're going to pretend my hand is not a hand right now. It's muscle. My long, skinny fingers, I don't know if they're really long and skinny, but for this example they are muscle cells. These are muscle fibers. They're very delicate. Even though they can pull really well, they can contract really well, they're delicate. So my body wraps them up in fascia. In saran wrap. It's obviously not really saran wrap, but it looks a lot like it. It wraps up. This is endomysium. I wrapped up one cell. Here's endomysium again. Okay? Wrapped up another cell. Here's endomysium again. Wrapped up another cell, right? But I want to keep all these guys together so they can they'll be even stronger. So I'm going to take all of these cells, and it wouldn't just be 3, by the way. It'd be a lot more than that. But I'm going to take them, all these individual fibers wrapped in endomysium, and I'm going to wrap all them together in paramysium. Just another layer of fascia. Now they're all together. They can still pull, but they're all kind of kept together. And then if I put both my hands together and wrap all that up, oh jeez, and wrapped all that up, so groups and groups and groups of stuff, that'd be epimysium. Yeah. It's just fascia. They're just different names for fascia wrapped around fascia wrapped around fascia. It's bundles, like individual fibers turned into bundles, a whole bunch of bundles together, and a whole bunch of bundles wrapped together. That's all it is. By the way,
that end would hook onto bones, right?
Oh my God! Quit stealing my thunder. What is this?
Sorry.
No. I'm joking. I want you to do that. What is this end called, Miss Monreal?
Tendon?
Yes. This is even more important, everybody. They say that you find tendon at the end of a bone and attaches at the end of a muscle and attaches muscle to bone, and it does. But is the tendon really just at the end of the muscle? No. It really is the place where there is no more muscle left. There is tendon, we don't call it that, we call it epimysium, endomysium, and paramysium, and all this other stuff, but there's fascia throughout the entire muscle. This is the same stuff. It's not like we glued the tendon on the end. It is just the place where it comes off the end. This is a very real-life example of what a tendon really is. Which is why when I pull it, my whole hand comes.
Through there.
Yes.
It's all woven, then it comes together, and then that's where it does the Spider-Man thing. And
Yes. Yes. And then there's fascia around the bone, and it Spider-Man's into the bone.
Okay.
Yes.
Cool.
Yes, it is cool.
Sorry, is fascia the tendon then, or is fascia around?
Yes. Fascia is the tendon. So let me give you Let me give you a different way to look at it.
You go by, was it periosteum that covers the bone? And is that the right word?
Yeah.
And then that's what the Spider-Man hooks onto the periosteum?
Yep.
Okay.
And the reason for that is that if I just drilled this into a bone, it'd be very easy for this to pop off. But if it's woven into fascia around the bone, it's very hard for it to come off because it distributes the weight very well. Does that make sense or maybe not? Sorry, I'm having problems with my fascia here. There we go. So what I mean is, if this other arm is my bone, and come on, work with me. I feel like I lost something. All right, hold on. If this bone is also wrapped in fascia, and they bond together, and this thing pulls, it's pulling on everything and not just one little spot. So it makes for a very strong connection. This is your Spider-Man analogy, right? And so that's right, that's the periosteum. Osteo means bone. So it's the stuff wrapping around a bone. And Miss Petrie, back to your question, the tendon is fascia, yes. The tendon is fascia, it's not wrapped in fascia, it is fascia. But it's fascia that was already in the muscle. Remember, it just came off the end there and there was just no muscle left in it, so we have this thing that's kind of hardwired together, and it's all fascia. All muscle has fascia in it. When you chew a steak, the fact that it has any chew whatsoever is the fascia. Muscles with more fascia in them are chewier steaks. But they all have it in there. So let me give you another way of looking at it. It might help, I hope. All right. Fascia.
I have a question.
Please. What's the question?
So why, if it's fascia, why does it have different names for it, for the...
Why do we call... Yeah, no, I know exactly what you're saying. Why? Yeah, I think I know what you're saying. Why do we...
Why is it epimysium, perimysium, if it's fascia?
Yeah. All right, can I ask you a question first? What's your I don't want the whole thing, I'm not trying to be weird. What's your address, your home address? Not the city, just like your address.
Like 7667?
7667 what?
West Vermont?
West Vermont what?
West Vermont. Avenue?
Avenue. Okay, so you live on an avenue, right? Ms. Torres?
Yes.
You live on an avenue, right?
Yes.
Do you live on a road?
Yes.
Do you live on a street?
No, on an avenue.
But what makes it different from a road or a street or a drive or a way or a place?
No, on an avenue. Or what do you...
I'm asking, I'm trying to make a point. I'm just playing with you. But what makes your avenue different from a drive, a road, a place, or a street?
I don't know. The street?
So is an avenue made out of asphalt? Blacktop. Ms. Torres? Ms. Torres, is an
Yes.
okay.
No.
It is like the stuff that you drive on, the asphalt, right?
Yeah.
Okay. Is a street made with asphalt too?
Yes.
Yeah. Is a road made with asphalt too?
Yes.
Right. So we give them different names, not based even on what they're made out of. We give them different names to help distinguish where you might find them, how short or long they are, things like that. My point that I'm trying to make to you is you said, why do we call this stuff by different names? The same reason we call streets by different names, so we can help tell them apart. But they're all streets. You were driving on, they're all made out of the same stuff. When I get on your avenue, it doesn't look different than my place, right? It's the same material that built it. We do it for convenience. Does that make sense? So when you say, like, why do we call these things different things like epimysium, endomysium, paramysium, I could ask the same question. Why do we call a street, an avenue, a place, a drive, whatever? You're right, they're the same stuff. We call it because of where they're found and other things we're trying to make. So we call fascia wrapping around a whole muscle epimysium. We call fascia wrapping around a group of little fibers paramysium, and fascia wrapped around a single fiber endomysium. We call a street that goes in a dead end a court. We call a wider street quite often an avenue. We call a narrower street a road. But they're all the same thing, right? We're just trying to designate how they change a little bit. Does that make sense?
Because I guess if we didn't have the different names for them, how would we refer to them? We would be like, wait, are you talking about that one? Are you talking about the muscle fibers? So we need the different names to distinguish exactly what we're asking or talking about, correct?
Yes, but I love the analogy I just gave because the fact is all roads are essentially made out of the same material, right?
Yes.
But it's convenient to us to call them different names because we mean slightly different things about where you might find that material, right? If you hear avenue, you think it's probably a little bit bigger. Well, actually in Phoenix we use avenue to mean, on the west side, and streets to mean on the east side and things like that. But they're all made out of asphalt. They're all made out of that blacktop material. Same thing is true with fascia. I hope that helped, Ms. Torres. I wasn't trying to frustrate you. I was just trying to give a neat analogy. So, everybody, you see this? Yeah? I know it's saran wrap, but say fascia. Fascia. Thank you. Bear with me. Stay. And stay with me. Now, I folded it over on itself a couple times here. Right. One more time. Hold on. Trust me. There we go. This is actually one of the most important discussions we can have in massage therapy. So I took that fascia. I folded it over on itself several times. Is it still fascia? Absolutely, it's still fascia. More fascia than it was before, but it's still fascia. But now it's a broad, sheet-like, tendon-like fascia, and we call this an aponeurosis. Is aponeurosis made out of fascia? Yes. But it's broad and sheet-like. Now let me show you something. Now, is this still fascia? Absolutely. We haven't added anything else to it, but it's a ribbon-like fascia, and we call this retinaculum. Now I'll explain why, just like the streets a little bit, okay? The broad sheet-like fascia that's called aponeurosis, our body uses to cover our stomach and our lower back and the top of our head. And it uses it to stabilize these places. We'll get into that later. But it wants a big, broad thing to weave a lot of muscle into. And we just call that fascia aponeurosis, but it's still fascia. Retinaculum, I find a lot of it around my ankles and wrists. And honestly, just like when you see gymnasts wrap up, if you tore off my skin, you'd see retinaculum that looked like that. What does it help do? It helps protect my wrists and ankles. But it's fascia. By the way, if you take this retinaculum, twist it up, is this still fascia? And I hook two bones together with it, what's this?
Ligament.
Ligament. Is a ligament fascia? Yeah. So you can describe this in different ways. You could also say that an aponeurosis is tendon-like, like a sheet-like tendon, and retinaculum is a ribbon-like tendon, and tendon is but it's all fascia. It's all fascia, or it's all tendons, or it's all ligaments, or it's all aponeurosis, or it's all retinaculum. It's all the same stuff. Literally, it's just put together differently and in different thicknesses. This one, this ligament, is terribly strong and really hard to pull apart, which is why it's really hard for my body to pull apart. Other ones do different things, but it's all asphalt. Just different streets, avenues, drives, all that kind of stuff.
I really like that example, and especially how you showed that it's so strong, because if you were to unwrap it, it would still be like the flimsy saran wrap, but when it's like...
Yeah. I literally, as a grown man, cannot pull this apart. As a grown man. And your fascia is more amazing than this. Like, the stuff is strong. And it's got fibers in it we're going to learn about later that actually give it certain types of directional strength. So in ligaments, the directional strength is this way. It's designed to hold stuff together. Your aponeurosis, it tends to go multiple directions because it does different stuff. But it's all fascia. And remember, what was the number one connective tissue? The number one tissue in your body was connective tissue. So of the 4 tissue types. Because fascia is wrapping around everything. It's what gives you strength. And what's so beautiful about fascia, it gives you strength, but what? It's still flexible. I mean, this is amazing even what saran wrap can do. I can do this, but I can't do this. That's exactly what I want in my body. So at a joint, this joint bends beautifully, but will not come apart. Bends beautifully, but will not come apart. That's what ligaments do for you. Right? But your body's really secure, so it wraps the outside of the joint with some fascia, by the way, that's really a synovial membrane. And inside it's got fluid to kind of keep the whole thing going. Everything's fascia. I mean, I'm exaggerating a little bit, but everything's fascia. When in doubt, just say fascia and you'll probably be right. Okay? And when you guys bite into a steak or a chicken and you get gristle, that's fascia. Yes. When Mr. Kandaris shredded his chicken, the reason it shredded was the paramycium around the bundles of muscle fibers split along the lines of the fascia. The fascia wouldn't break. So what happened was he got these long strands. That was the muscle fibers wrapped in fascia. It was ripping along the strands of fiber. The individual ropes were coming apart. But it wasn't even the individual cells. It was groups of them still because the cells are so small. But that's why you can shred chicken. It's shredding because it's wrapped in fascia and it's coming apart where there isn't fascia.
I think I actually just found some in my sandwich.
Yeah, that's fascia. Disgusting, but thank you.
It doesn't chew, like, you know, can't really chew through it.
Yeah. The stuff is tough, man. And you want it to be tough. Cool. All right. I'm going to move along. But I think that was time really, really, really well spent. I apologize if it was slow. But I can't emphasize how important fascia is to a massage therapist. In my opinion, it's more important than the muscles. But also, that's kind of a stupid statement too, because you can't really talk about a muscle without talking about fascia. Because there's fascia running through the entire muscle, wrapping around the entire muscle, wrapping around groups of muscles, wrapping around every muscle fiber, and using it to tie it to a bone. And the bone's wrapped in fascia. And by the way, bone isn't just wrapped in fascia. There's a fascial network inside the bone that's filled in with calcium and potassium that makes the bone strong. Everything's wrapped in fascia. Everything. All right. You guys know what origins and insertions are, right? Origins generally attach to the thing that moves less. So in general, not always, in general, the origin is closer to my center of my body because this part's not moving. The insertion's out here, and that's where what moves. In general, it doesn't always have to go that way. Remember we were talking about the trapezius? Trapezius had an origin here, insertion down here. This moves, but we found out sometimes what happens. Sometimes the origin can move too. So I say in general, it's the less movable part. I just call both of these attachments. But if you want to get more specific about an attachment, the origin is the part that tends to not move. The insertion is the part that tends to move, but they can switch places. However, when they switch places, we don't switch names. This is still the origin. I wish they just called all attachments. Because all I think about in kinesiology is these 2 points come closer together. Whether I'm doing this or this, my ear got closer to my shoulder. Either way, those 2 things came together because muscles can only contract. And muscles can only contract because sarcomeres can only contract, which are the tiny little train cars in the muscle. Okay. All right. And by the way, what I just showed you is called functional reversibility. This and this is functional reversibility. It means the function can reverse. Don't overthink it. Don't overthink it, please. It just means like, hey, if I'm pulling on both these parts and this one doesn't come up, then this one's going to come down. If this one doesn't come down, this one's going to come up. That's all it means. If these 2 things have a magic thing between them that pulls them close, this one's got to come over here or this one's got to come over here. They both have to meet in the middle, something. Functional reversibility. That's it. Don't overthink it. This is a really good picture because this is kinesiology 101, right? You've got a muscle hooked up here. Don't worry about. By the way, what muscle is this? Who can tell me what muscle we are looking at right now? It should be obvious.
Bicep brachii?
Bicep brachii, yes. We know that because it's going up over the shoulder, the long head is, to attach in the supraglenoid tubercle. We can't see the other side of it because we'd see the short head going into the coracoid process of the scapula. But anyway, it hooks down into my arm here, and so when it contracts, it pulls my arm up. That's how it works. The muscle belly contracts and pulls my arm up. That's how it works. My lever is my arm. By the way, we're about to talk about levers. The fulcrum is my elbow. We're about to talk about levers, and in levers they talk about fulcrum, and a fulcrum is just the thing that the lever pivots on. Right now, this hand is the fulcrum. My elbow is the fulcrum. It's where the lever pivots. If you're on a seesaw, the fulcrum's in the middle. The fulcrum is just where the lever pivots. Right? Now, I will say this because it's important to think about, even if you don't kind of get it completely today. If I am lifting up something very heavy, let me put a fulcrum here. I don't like that pen at all. All right. This is my fulcrum. This is my lever. This is a heavy object. The closer the fulcrum is here, the easier this object is to lift from back here. If it's way out here like this, it's actually very hard to do. The closer it is to here, the easier it is. And I'm about to tell you everything I think you need to know about levers as it applies to kinesiology, and I don't think this is in the book. So I advise you to pay attention. Can everybody see this fulcrum? Okay, it's important. This is actually really cool, and it kind of explains levers completely. We've got a lever here. The long side's over here. The short side's here, right? Can we see that when this side goes way down to here, that this side will only come up to here? Right? We've got this really long lever. And watch this. Look at how, can we all see this? I'm going to bring this down, 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 down. How much up did that do? 3 inches? This came down over a foot. How much did that come up? A little bit, right? Do we see this? I just need to know that you see that this comes way down and this one comes way up. A little bit up. By the way, this one goes a little bit down and this one goes way up. You can flip it. Cool. So the way a lever works, it takes all this distance and turns it into power. If this comes down 12 inches, but this only goes up 3 inches, where did the 9 inches go? They converted to power. If this goes down 3 inches, and this one went up 12 inches, my power converted to speed. It went to distance. So, if I want to lift something really heavy, I want a big lever out here. It's going to be very easy to pull because I might bring it down 100 inches and only move this up 10 inches. Which means each 10 inches here was only equal to 1 inch of movement here. It means it's just a lot easier for me. But what did I do to make up for that ease? I had to move it farther. You can't magically move stuff. This thing always weighs what it weighs. This thing weighs 100 pounds no matter what. But the question is, do I lift that 100 pounds over 100 inches? Or do I lift it over 10 inches? Levers convert distance into power or power into distance. This is super easy to pull down, but I have to go a really long way. This is actually hard to pull down, but I go a long way. It's heavier, but it goes a long way. That power goes into distance. This is super easy, and it doesn't move very far down here, but it goes into power. So levers trade off distance for power or power for distance.
Okay, so how is that applicable to muscles and our movement?
Thank you. Remember I asked you guys if you were built for power or for speed? And I said you're actually built for speed. Most of the levers in your body, let's see if they have this. Hold on. Oh, give me levers here. Stop. Oh, I'm going the wrong way. I couldn't figure out. I think I am. No, I'm not. Come on. Don't worry, everybody. Do they have classes of levers here? Yes. Is that a type 3 class? I think so. Yeah, class 3. Most levers in your body are class 3 lever. And a class 3 lever works this way. Actually, can you see me bigger if the slideshow's not up? Is that how it works? Let's stop sharing for a second.
I mean, I just pinned you to the screen.
Well, that works too. I like that too. All right. I turned off the slideshow for just a second. And cool. All right. So, let's talk about our arm, Miss Monreal. This is a forearm. Here's a hand. Right there. Beautiful hand. Everybody knows that's a hand. Almost looks exactly like a real hand. And then, we've got my humerus. Yeah. This is your elbow. This is the fulcrum. Yeah. If my bicep went way out here and attached there, it does not. I'm going to explain something in a second. It does not. But if my bicep shortened an inch, my arm would move up about an inch. Right? And it'd be very powerful, by the way, because I'm reaching way out there. It'd help. But it wouldn't be very fast. Instead, that's not where our bicep hooks. Our bicep grabs way down here. And if our bicep lifts this part up just an inch, how much does the arm go up out here? 6 inches. Because of how angles work. So, if this is my forearm and my bicep grabs way out here, it takes a lot to lift this up. But if I grab right here and I just lift a little bit, look how much this thing goes. I don't have to do very much here to get this thing to go way up. So I trade power for speed. It's a class 3 lever. I'm not too worried about that, but I've traded power for speed. Your muscles are actually ridiculously powerful. When I'm lifting 100 pounds with my hand, my muscle's actually pulling about 500 pounds or more. It's actually, the lever, it's not using a lever like we normally use a crowbar. It's using it the opposite way. It's trying to get speed because your muscles can't contract that much. They're just very good at it. And so when it pulls a little bit down here, the end part moves a lot. Let's even look at the back side. That's even more noticeable. Your tricep hooks to the back of your elbow. You've got that much lever back there, right? So it means like your arm's like this, your tricep attached to this little thing. Well, look, if it pulls that just a little bit, how much does your arm move? A lot. So my tricep pulls just a little bit, my arm goes a lot. Because it's pulling a little short lever that's moving a long lever. If I pull on a little short lever, look how much I move this lever over. I'm going to move this lever right here, down here, over 1 inch. How much did that move up here? 6 inches? I don't know, a lot. That's how the levers in your body work. You pull a little lever a little bit, and your arm goes really far. It's not a lever that makes you strong, it's a lever that makes you fast. I have to pull this really hard, but man, this thing flies. You're built for speed, actually, not power. Doesn't mean you're not powerful. It just meant your levers, there are other ways you can make your levers work much more for power. In fact, when we use levers, we take our crowbar, I put it into here, and I pry something open. Well, this is very slow. I've got to go down, 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 down. I just went down 18 inches to get this thing to move up 1 inch. But it's easy, and that's how I lift a heavy object. My 18 inches of effort went into 1 inch. That's how a lever works. Yep, and we'll talk about that more. I had to kind of introduce the idea today. But that is the concept of a lever, is a lever helps you trade speed or power for distance, essentially. We covered a lot of really, really big concepts today as far as I'm concerned. The fascia and the lever thing is huge. I think we should stop. I was going to go on, but I think we should stop. I think we've covered a lot today. I wanted to make sure I covered every last little thing that's going to be on you guys already did the book matching on your quiz, but I think you'll be fine. I think you'll be fine. Let's summarize things from today, because we have tomorrow. We can talk about this again, all that kind of stuff. Oh, hold on. I do have to do one thing that you're going to hate me for. Let's see. Come on. There we go. Bear with me. There we go. There we go. Cool. We will talk about muscles more tomorrow. And we have a tiny little 10-question quiz tonight. That's it. Because you've already done the end of chapter stuff. I think the 10-question quiz will be quite easy. But you do have, of course, a pathology, a muscular pathology to study. So let me present this now really quick. Window. Boom. Share. Okay. So, make sure that you're paying attention. You write down your pathology that you're going to study. Remember, path essentially means disease and ology means to study. We are studying disease. Anything with ology is study of. Anything with ology is study of. Path, disease, study of disease. So these are muscular-based diseases or muscular system-based diseases because some of them have to do with tendons and fascia and things like that, but the muscular system. So, Miss Hunter has tendinitis and tendinosis. What is the difference between tendinitis and tendinosis? Miss Hunter will tell us tomorrow. Miss Yanez has de Quervain tenosynovitis. And if she can say that tomorrow, that will be half the battle. Miss Torres has fibromyalgia syndrome. Miss Stanley has myofascial pain syndrome. Miss Petrie, oh, we better let her back in. What happened to you? Miss Petrie, yeah, don't worry about it. Can you hear me? Good, because we're about to, tomorrow you need to tell us about Osgood-Schlatter disease. I think it's German. Osgood-Schlatter disease. Miss Nguyen, you're going to tell us about plantar fasciitis. Plantar fasciitis. Cool? Can you see it? Good, okay. You'll love it. Plantar fasciitis, by the way, is something that you will work on. You'll have clients come to you with it, so it's a really good thing to study. Miss Monreal, you will have shin splints, which is an interesting thing to report on because shin splints have a technical thing they are, and then there's something that people think they are that they're not, but they use the term for that. So, shin splints. Just check out shin splints. Mr. Kandaris, you are going to talk to us about strains, but I also want to know what makes them different from sprains. Strains and sprains. Yeah. Miss Harper, you're going to do tenosynovitis. Miss Hanson, epicondylitis. Aren't these fun words? Epicondylitis. Miss Felix Osuna, tension headaches. How many clients do you think are going to come to you with tension headaches? A lot. Miss Cooper, torticollis, and Miss Bilotic, whiplash. So, 10-question quiz and these assignments. Did anybody not get their assignment? I can go back to their slide. We're good?
Can you just say it one more time for me, please?
I'll try. Let's see. Let me go back to it. Hold on. De Quervain tenosynovitis. I think it's de Quervain tenosynovitis. I'm right about the tenosynovitis, but I think it's de Quervain. Yes, de Quervain tenosynovitis. I also, for all of you, you can type this into the internet and say, how do I pronounce de Quervain tenosynovitis? And somebody will come on and say something completely different. No, hopefully they'll say de Quervain tenosynovitis. The really cool places even have like 3 different people saying it because it's all, you know, it kind of depends on your accent. It is, de Quervain tenosynovitis is a type of tenosynovitis. It's why I actually had Miss Hunter go first. I didn't originally have her going first. I had you guys in reverse alphabetical order, but I wanted her to cover some stuff that might end up affecting your thing. So, we'll see. Don't worry about that, Miss Hunter. Just do your thing. But there was a reason for that. Anyway, cool. Yeah? Yeah. So we covered a lot of heavy-duty concepts today. Yeah. Let's stop presenting. Let's try to wrap this up a little bit. For your sanity. Your sanity. Yeah. Okay. So let's summarize some stuff that we learned today. By the way, the class honestly gets easier as we go because we get kind of all this stuff out of the way with. It really does. We're only on day, 21 or something? Okay. Okay. Miss Yanez, there is fascia wrapped around an entire group of muscles. I mean, it's kind of the topmost layer of fascia. And what do we call that?
The epicene?
Yep, epimysium. Epimysium, yes. Miss Felix Osuna, what do we call the fascia that's around all the muscles, like groups of muscles?
Is it the one that starts with the ED?
No, Miss Yanez just said it. I'm just drilling you guys right now. It's epimysium. Epimysium. So say epimysium.
Epimysium.
Thank you. Mr. Kandaris.
Yes.
What is the fascia that goes around an entire, like multiple groups of muscles? Top layer fascia.
Brain partner.
Just to help you guys out, I asked the same question over and over again. So I just asked Miss Yanez and Miss Felix Osuna. Miss Yanez, what's the fascia that goes around the entire muscle?
Epimysium?
That's correct. Miss Felix Osuna, what is the fascia that goes around the entire muscle? Epimysium. Mr. Gandaris, what's the fascia that goes around the entire muscle?
Epimysium.
Thank you, sir. Miss Cooper, what's the fascia that goes around the entire muscle?
It's endomysium. Oh, my bad. It's epimysium. I'm sorry.
Miss Yanez, what's the fascia that goes around the entire muscle?
Epimysium?
Thank you. Miss Felix Osuna, what's the fascia that goes around the entire muscle?
Epimysium.
Cool. Mr. Gandaris, what's the fascia that goes around the entire muscle?
Epimysium.
Miss Cooper, what's the fascia that goes around the entire muscle?
What, epimysium?
Epimysium. I'm not trying to make fun of you. I'm just drilling this in until we get it. It's like in our head perfect. Cool. Thank you. Miss Monreal, what's the fascia that goes around the entire muscle?
Epimysium.
All right. Now, Miss Monreal, we know that there's smaller packages in there, right? So if we drop down a level into a bundle underneath this epimysium, what's that next fascial bundle? What's that layer called?
Paramysium.
Paramysium. So what's the top layer called?
Epimysium.
And what's this next layer called?
Paramysium.
Thank you very much. Miss Torres, what's the top layer of fascia called?
Epimysium.
Yes. What's the next layer called?
Paramysium.
Thank you very much. Miss Harper, what's the top layer called?
Epimysium.
Thank you. What's the next layer called?
Perimysium.
Thank you very much. Miss Nguyen, what's the top layer called?
Epimysium.
Yes. What's the next layer called?
Perimysium.
Perfect. Miss Hanson, what's the top layer called?
Epimysium.
What's the next layer called?
Paramysium.
And what's the last layer called? The one that comes at the end.
Endomysium.
Oh, that's kind of convenient. I didn't realize that ever before. Endomysium and end. Cool. So what were those three layers again, Miss Hanson?
Epimysium, paramysium, and endomysium.
Thank you so much. Miss Petrie, what's the top layer called? Where did she go? I think she just actually kicked herself off. Okay. We will come back to you. I think she literally flipped herself. Okay. Miss, oh, you're back. Oh, thought you were trying to snake out of me there.
Okay, sorry, I pressed the wrong button.
I did it yesterday at a meeting where I literally went to talk to somebody and I turned myself off. So, what's the top layer called, Miss Petrie?
The
Epimysium. Then what's the next layer called?
paramycium,
Yep. And what's the last layer called? The end layer.
endomycium.
Endomysium. That's awesome. Cool. Okay. Where am I? I feel like I've missed somebody. A couple of people. Miss Stanley. What's the top layer of fascia called?
Epimysium.
What's the next layer called?
Paramycium.
Fantastic. Fantastic, guys. I just want you to try. That's great. What's the last layer called? The end layer called?
Endomysium.
Beautiful. Beautiful job. Thank you. Miss Bilotic. What's the top layer called of fascia?
Epimycium,
Yep. What's the next bundle called?
paramycium.
Yep. And by the way, hold on one second. Everybody realizes that in the epimysium, there's lots of bundles of paramycium, right? The epimysium is holding lots of bundles of paramycium, right? And then the paramycium is holding lots of bundles. What's the last layer of fascia, Miss Bilotic? The end layer?
The endomycium.
Yeah! The endomycium. Cool. Awesome. Miss Yanez. The endomycium can be wrapped around a single muscle fiber. Very simply put, what is a muscle fiber? What's another word that I could call a muscle fiber? I'm thinking of a four-letter word. A muscle fiber. Yeah, go ahead. What?
Actually, I don't know. I was gonna say, is it the thin myofibers?
Don't go there yet. We're still bigger than that. But what is a muscle fiber? It's also a muscle. Anybody? Cell. It's a cell. Muscle fiber is a muscle cell. By the way, Ms. Jonas, I apologize. It may not have been clear what I was asking for, but the point is I just want people to realize a muscle fiber is a muscle cell. It's a very long, stretched out cell. Cool? So, Ms. Jonas, what's the top layer of fascia?
The epimysium.
Yep. It's wrapped around a whole bunch of bundles that are wrapped in, what's the next layer?
Paramycium.
Yep. And that has a whole bunch of small bundles in it that are wrapped in
Endomycium.
endomycium. And those are around individual muscle fibers, and an individual muscle fiber is also called a muscle
Cell.
Thank you. Cool, cool, cool. All right. Miss Felix Osuna. Miss Felix Osuna, what's the top layer of fascia called?
Epimysium.
What?
Epimysium.
Epimysium. Cool. And the next layer is called?
Paramycium.
And the next layer is called?
Endomysium.
And that's around a muscle fiber. What's another word for a muscle fiber?
Cell.
It is a muscle cell. That is absolutely correct. Cool. Awesome. Thank you very much. Mr. Kandaris.
Yes.
Top layer of fascia.
Epimysium.
Next layer.
Paramycium.
Last layer.
Endomysium.
Wrapped around a muscle fiber, also could be called a muscle
Fiber. Fascia.
Muscle fibers can also be called hold that thought for 1 second, sir. Miss Yanez. Miss Giannis, what can muscle fibers also be called?
Muscle cells.
Thank you. Miss Felix Osuna, what can muscle fibers also be called?
Muscle cells.
Thank you. Mr. Kandaris, what can muscle fibers also be called?
Muscle cells.
Thank you very much, sir. Mr. Kandaris, inside these muscle cells, there's kind of like long train car of these little pulling units. These little pulling units are inside the muscle cell, the muscle fibers. And these little pulling units have a name that starts with an S. Do you remember what it is?
Sarcomere.
That's fantastic. That's exactly what it's called. Sarcomere. Sacromere, I'll take it. Sarcomere.
Okay.
But that's right. I'm not correcting you. I'm just saying that's the way I say it. Sarcomere. Thank you very much. So just to cap off for everybody in case I ask them the same question, which I'm going to, but what's the top layer of fascia, Mr. Kandaris?
Epimysium.
What's the next layer?
Endomysium. Oh, paramysium.
Cool. So wait, we've got epimysium, then we've got these little paramysiums. Cool. And then what's the little stuff inside there, the last layer?
Endomysium.
Endomysium. Inside that is muscle fiber, and another name for muscle fiber is what?
Muscle cells.
Muscle cells. And muscle cells have long chains of contracting units, and those contracting units are called what?
Sarcomeres.
Thank you, sir. Miss Cooper, what are the contracting units called inside muscle fibers or muscle cells? What are the contracting units called? That is correct. Thank you so much. Miss Monreal, what are the contracting units that there are thousands of all chained together, hooked together by little Z's, called inside muscle fibers or muscle cells?
Sarcomere.
Yes! Miss Torres, what are the contracting units that are inside long muscle cells or muscle fibers called that are connected by little Z's? What are they called?
Sarcomere.
Yeah, we'll take it. Sarcomers. Cool. Miss Harper. That was so nice of you. Miss Harper, what are the little contracting units called? There's a whole bunch of them stacked together inside a muscle fiber, inside a muscle cell. They're the same thing. What are they called? Sarcomers. Thank you. So, Miss Harper, don't turn off your mic yet. Let's review for everybody. What's the top layer of fascia called?
It's the epimysium.
Yes, it is. What's the next layer here called?
It's the perimysium.
Yes, it is. What's the last layer here called?
Endomysium.
Yes. What's another name for a muscle fiber that those are wrapped around?
Muscle cells.
Yes. Inside the muscle cells, there's a whole bunch of contracting units called what? Sarcomers. Yes. Yes, yes, yes. Miss Hanson. Inside the little sarcomers are what? I don't care what word you use. I don't care if you talk to me like I'm 5. Yes. Little filaments. The thick and thin filaments are in there. The myo just means muscular. The muscle filaments. So thick and thin filaments are in there. Right? What you said was perfect, by the way, but let's call them thick and thin. They're thick and thin myofilaments. That's the truth. Thick and thin myofilaments are inside the sarcomeres. These are the things that do this, right? Cool. So, Miss Hanson, what's the top layer of fascia?
Epimysium.
Yes. What are these bundles down here, second layer, called?
Paramysium.
Yep. What are the little bundles inside the paramysium called?
Endomysium.
Yep. And those are wrapped around individual muscle fibers. What's another name for individual muscle fibers?
Muscle cells.
Yeah, muscle cells are really long, and they've got all these little contractile units in them that each one of them can contract, and they're connected together like railroad cars with these little Z's. What do we call those contracting units?
Sarcomeres.
Yes, we do. And they contract because there's little things inside the sarcomeres that actually contract and that kind of grab on each other. What are those?
The thick and thin
Myofibrils?
filaments.
Yep. Thick and thin myofilaments is fine too. Myofibrils or myofilaments. But anyway, the thick and thin things. Yeah.
Okay.
Cool, cool, cool. Miss Hunter. Miss Hunter, what is this layer here called?
The one that wraps around the entire thing?
Yes, ma'am.
Epimysium.
Yep, and what's the next layer?
Paramysium.
What's the last layer called?
Endomysium.
Yep, it's wrapped around,
Muscle cell?
yes. What's another name for, let's flip this on everybody. What's another name for muscle cell?
Oh God. Fiber, muscle fiber.
Yeah! Muscle fiber, muscle cell. Thank you very much. It's got a whole bunch of contracting units inside it.
Yes, they're called sarcomere.
Yes, they are. And the way they contract is they've got a whole bunch of little filaments inside them. Yeah? I kind of gave the answer away, sorry. Are the filaments, there's two types.
Thick and thin.
Thick and thin, made with actin and myosin. The thin ones are, no, I wasn't asking that. You did the right thing. Actin makes up the thin, myosin makes up the thick. Right?
Mm-hmm.
Cool. Who can tell me what ion gets pumped in there to turn them on, to make them actually contract? What ion? I'm going to have a glass of milk while you guys think about it.
Yeah, calcium pumping?
Oh, calcium. Calcium ions. That's what does it. Yeah. Calcium ions turn them on. And that's why they contract. Yeah. And that is essentially everything we covered today. And that brings us to 11 o'clock. And I really appreciate your engagement today. And we covered lots of really, really important stuff. Probably the fascia was more important than all the stuff I just covered just now. But we got a real huge toehold in some of the most important stuff in kinesiology. It's all going to come together later. It's going to be amazing. But I think you guys actually have a clear conceptual understanding. I don't care about the words. A conceptual understanding about how things are bundled together in your body, how they essentially pull. You guys did absolutely fantastic. I will release the quiz right now. You have a 10-question quiz. And I'm sorry I didn't release it earlier, but we covered so much stuff. And tomorrow we do need a brief presentation on your pathology. Yeah? But I'll release the quiz now. You are welcome to stay on. If you have questions, you're also welcome to go. Whatever works for you. I look forward to seeing you guys at school later. Thank you. Thank you, thank you, thank you. Let me release the quiz here. There we go. Boom. Quiz is open. All right.